So it's my pleasure to introduce our first plenary, Gerhard Fettweis, who you just saw has been awarded the Fellowship of Eurosip. It's kind of appropriate. I've known Gerhard for a long time. Our relationship seems to be based on trading insults in a nice, genial way, I should add. But I'm going to be nice to him for a change. And it's very appropriate that Gerhard not only becomes a fellow of Eurosip, but actually presents one of the plenaries, because his late father, Alfred Fettweis, was, of course, for those of you who don't know, a member of Eurosip from its very inception. And I'm sure he would have been very pleased to see his son become not only a fellow, but also deliver a plenary at Eurosip. So Gerhard was awarded his PhD thesis from University of Aachen in 1990. He spent a year in IBM research in San Jose in California, moved to TCSI in Berkeley. But since 1994, he's been the Vodafone Chair Professor at TU Dresden in Germany. And for those of you who want to know the effect Gerhard has had, over 20 companies from Asia, Europe, the US are sponsoring his research on wireless transmission and chip design. He coordinates 2 DFG centers in Dresden, and he has spun out 11 startups. Yes, that's 11. So it's a man who has too much time on his hands, clearly. And his research is very much focused on communication systems and the implementation of the signal processing algorithms which are at the core of it in the development, particularly for 6G. So it's my honor to ask Gerhard to present his talk on designing 6G and AI, navigating the challenges and bridging the implementation gap. So please welcome Gerhard. And he's wearing his Eurosip tie.
It only took me 3 tries to get the tie knotted. I'm not used to it anymore. But I think I managed. There we go. Thanks. So, first of all, thank you for these nice words. Thank you, everyone, for giving me the chance on the behalf of the 4 of us to basically be here and give a keynote as one of the 4 new fellows. And thank you very much for this honor. This is really a big honor. For me, Eurosip and Eusipco has this very special meaning, because my very first Eusipco was in 1988. It was my 2nd international conference that I attended against the will of my PhD advisor. He said, "You're not going." I said, "I am going." I said, "I submitted a paper." He said he didn't want me to submit a paper. So in the end, I paid out of my own pocket and went to Eusipco. And my dad was nice enough, he said, "Let's make it a road trip." So he came, I came to Cologne, and he picked me up there in the car, and we made it a road trip, the very first road trip of my dad and myself to a conference. We did this again later on to ISCAS in New Orleans, if you remember ISCAS in New Orleans, a couple years later. So this is, and the reason why I said Eusipco is so important, against the will of my PhD advisor, I said, he wanted me only to attend US conferences because he said that's the only thing that's important. But I said, maybe my career will be later on in Europe, even though I did move to the US for the first couple of years. I said, I might want to move back to Europe, and I have to network. And this I love about this conference. It's about networking, getting to know people, et cetera, and I did network. I networked here in Grenoble, next door, in '88 with Fujitsu, and I networked so well that the Fujitsu guys came and they financed his startup, my PhD advisor's first startup. So that's why not too bad in hindsight. Just to give you some facts, this is my chair. We've done all kinds of things. I want to say thank you to those that sponsor us and that are project partners. Here's the list of startups. These are 11 startups, maybe a little more, 19, I think, in the meantime. And we've actually not only started tech companies, but also non-tech companies like Kletter Arena and Ruby Liquor. So just to know that my team does these kind of things as well. And why do they do that? because to start a company in Germany, you have to put down 25,000 euros in cash, and they didn't want me to put this up, my PhD students, but said, no, we'll work for it, so they did all these other things besides that. Some of these has been sold and are in the hands of others. And obviously, those that have an iPhone 7 and beyond, if it so shows 4G, that's, for example, our 2008 startup Blue Wonder that we sold to Intel. Now, I want to talk about the implementation of signal processing. And I will spare you of a couple of the detailed equations, but I want to give you the gist of what that means. And for that, let's first visit wireless. 5G was ultra-reliable, low-latency communication, the tactile internet. What does that mean? If I want to balance a ball remote-controlled, or if I throw a ball with 10 meters per second, which is not very fast, it's a centimeter per millisecond, I have to grab it with 1 millisecond precision, with 1 centimeter precision. This is what I call the tactile internet at some point in time and started the whole shebang. After doing that, I said, okay, besides having PhD students, let me have an implementation team at the university, engineers that don't want to do a PhD, just want to see how we get things going. So we have teleoperation projects in agriculture, in construction. We are out there flying drones. We are driving cars. We have campus networks. You see here our trailer. We have 5 of these trailers. We set them up spontaneously and can set up as campus networks and do measurements for the, like here for the German regulator, BNetzA. We have, here you see a couple of our sites that we have in different areas around and in around Dresden. We are in a winery, we are in an orchard, we are all over the place. And we're on the airport Leipzig, which is the biggest cargo hub in Europe because it's the DHL hub. And I don't know how many hundreds or thousands of airplanes come in at 11 p.m. every night and leave again at 1 to 2 a.m. in the morning. And in that sense, and we have the whole thing in an explorative 5G network, getting our hands dirty. Now, this is not research. Why do I do that? Because if you feel a little bit responsible for the specification of 5G, I felt we have to find out where are the deficiencies. What is going wrong? What is going right? And what do we really need to understand to define 6G in the right way? And finally, the last thing is our new project, the Smart Mobility Lab. There's 1,000 square kilometers of use space around Dresden, as you can see here, and in and around Dresden. And we are there and doing all our drones, flying our drones, and doing the 5G network there as well. So in the end, if you look at this, we have close to 200 use cases with more than 50 companies that we collaborated with and tried out the 5G network and continuously trying out this 5G network. So with that, we're ready for 6G. So what is 6G? I give you my personal view, which is not necessarily everyone's personal view or company's view. It's my personal view. So we had 2 generations of voice, 2 generations of mobile internet, and 2 generations of motion control. No, we had 1 generation of motion control. But why do we always need 2? 1G was what? Voice telephony. 2G was voice telephony. What was the difference? Actually, while we had 1G, we whet the appetite of the consumer and gave them cordless. And if you remember, those that are old enough, at that time, people said consumers don't need cellular. Cordless is good enough. There were telepoint services with Packbell in Walnut Creek and with Deutsche Telekom in Dortmund, and these telepoint services thinking you just have a decked cordless hub at every payphone and everybody can run to the payphone and connect and everything is good. You can place a call. But then it was not good enough. Even though there were so many payphones, and think of it, there were all these payphones here in France especially. But I can place a call, but how do I make sure that the termination point, the person I'm trying to reach, actually walks towards a payphone so that she or he has coverage and can connect? And so the value of being always available, not only to place a call, but also to be called, is what really makes the difference. And that's why 2G really took off as a consumer phone in our pockets, low power, low cost, available everywhere, and that made it happen. Then we thought, wow, 3G. We'll just add the camera and make it a video phone. That's what it was not. If you remember the clamshell 3G phones from Ericsson and whatever, they had a camera looking at you, but that was not for selfies. It was actually for video calls. Very lousy video calls, €2.50 per minute, totally crazy. What really took off was email with BlackBerry and Nokia Communicator for business customers. Hardly anybody bought a BlackBerry as a private consumer. And what we had as consumers, suddenly Wi-Fi popped up and we had mobile internet, untethered internet at home. The same thing as with cordless, whet the appetite of the consumer, and then shrunk the PC into the hands of us into what it became, and that's the smartphone of today. Now, what is 5G? A little bit faster data. No, if you look at all the use cases I showed you, those were all business customers. So it's all about business and business customers. And again, we're whetting the appetite of consumers. How? For mobile robotics and virtual reality, moving real and virtual objects. Just look around. Your vacuum cleaner, your lawnmower, these little things, you're getting used to it. To have mobile robots whizzing around, virtual reality, augmented reality is happening as we're speaking. And so 6G is going to be big in opening the door to personal mobile robotics. It's going to change our entertainment, our gardening, our daily chores. The kids don't have to clean up rooms anymore. There's going to be a little robot cleaning up the rooms. The Legos are going to be sorted. Mobility, any kind of machinery tools, health, fitness, whatever all. It's amazing. It's really going to be a new world of connected mobile robotics. So what is it about? The consumer. Now we have to start thinking. Because what does that mean? There are certain parts that we as signal processing algorithm designers have to think about, which is exactly the implementation gap. There's the theory, and there are the algorithms, but there's the implementation of hardware and reality, and often enough, that gap is two communities that don't talk too much, and therefore let's address this. So the first thing that we have to think of is, what was it? We had these big clunky Nokia Communicator or these big clunky portable phones in 1G. It is getting the energy down. And for this, it's about coming up with crazy new ideas. Now, I propose this, and please think of other solutions as well, the gearbox approach. And what does that mean? Well, if we look at the energy consumption at the base station side, at the operator side, not in the terminal, but just look at the base station side. Yes, I mean, the RF consumes 29%, air conditioning consumes 29%, and the rest is another 1/3 of the power control. So, but if you look at that, the radio access network is 75%. The core network is not very much. Data centers and these kind of things are there as well. So we really have to start looking at the radio access network. Amdahl's law tells us, try to attack that part first. That is eating up most of your budget. And if we can reduce 1 watt of power consumption, we can reduce 1 watt of air conditioning. So it's actually 2 watt we gain. Now, if we look at cellular data, it happens all over the place. It's in an area distribution that is spotty. It's not uniform. And if you look at many of the cellular algorithm designers, what do? We say there's a full buffer at every base station, and we assume there's a full buffer, and now we try to maximize the data rate. Why do we want to maximize the data rate in these deep blue places? And if you look at it here in Manhattan, even in Manhattan, a very dense urban city has a very uniform spatial distribution. What is it? As is known, it's log normal distribution. This is the model that has been in the world since the 80s. And if we look at this and measure this, again, it's log normal distribution with different, of course, parameter settings. But if we look at a log normal distribution, what does that mean? It is a long tail distribution, and that means 99% of the time we're in low data rate modes. Either areas or the base station over time is in low data rate. And if you look at this also from a measurement by Nokia Bell Labs, published at the Wireless Smart Antennas this year, we see that basically 50% of the traffic is taken away or is carried by 10% of the base stations. 30% of the traffic is carried by another 10% of the base stations, et cetera, et cetera. So we see that 80% of the traffic is carried by 20% of the base stations. We see again this kind of a distribution, even though what? We know that the distribution of base stations is like a Poisson point process distribution in space. So to maximize, to level out the use of the different base stations, right? We want to make them all uniformly full, but that's not true. Even though we have them sort of located more densely where we have more dense traffic, we don't get it done that way. And then we have another thing to think about, which is silicon. Silicon has a property that most people forget that don't do chip design. Once you reach 300 to 600 megahertz, we have an issue. So if you look at the ADC bottleneck here, Boris Moorman's statistics, and we look at this over the last 33 years, we see, wow, the power consumption goes down. The x-axis is the clock frequency, and the y-axis is the femtowatt per conversion step. A figure of memory, femtojoule, not femtowatt, sorry. And so what we see, if we know if we double the clock, we double the power. If we triple the clock, we triple the power. And silicon is improving, but not that well anymore. What is the other problem? This one. As I say, around 300, 600 megahertz, silicon has a property that it goes from this linear to a nonlinear point of operations. It becomes quadratic. And this is often forgotten. So if we take this kind of situation, what do we need to do? Actually, the power consumption, if we go beyond 200-300 megahertz, which is what we're going to be doing at 6G, because we have more than 200-300 megahertz of bandwidth, we have an issue because amplitude becomes really an issue. We would actually want to do just 1-bit ADC because the automatic gain control is the one that eats our juice. If we did that, we would do only zero crossing modulation or even go to impulse radio. Now, this sounds really weird. Impulse radio in the times of NOMA. But if we look at this, in this kind of approach, let's assume we have 4 different transceivers. One for low spectral efficiency, availability, so we have to crunch everything out of the spectrum. But that is only possibly the case in 0.01% in the area and time. And if we consume 100 times more power, well, 10 to the minus 4 times 100 times more power is still 1/100th of the power. If then in the medium rate we use not NOMA but regular linear QAM, OFDM, MIMO, and this is only 1% of the time, then since it's only 1% of the time, it's P divided by 100. And if we then go on and go to some kind of just zero crossing modulation or impulse radio, we can get to, in total, to about 100x improvement in power consumption. But that means not one radio, not one ADC. We need to have 4 different modems sitting next to each other. And we have to not 4-fold the silicon, because of course only the high rate, NOMA, is really eating up square millimeters on the die, but we really have to make sure that the others eat also a little of real estate, but it's maybe 10, 20% additional cost. So now the question is, if we have this kind of approach, how do we estimate from another approach. That what I showed you was very back of the envelope. So what we've been doing is trying to understand M quadrature amplitude, zero crossing modulation, impulse radio, sitting next to each other and understanding the power amplifier, the mixer, the oscillator, the A to D converter, D to A converter, everything, low noise amplifier, every different component that you have in this kind of transceiver, including signal processing, and understand what do we allow. So we allow that an active gear, only that transceiver is on. It has a system bandwidth. It transmits at power PT, and we have the most brutal duty cycling. That means we can duty cycle whatever and instantaneously turn on the transceiver and instantaneously turn it off. Now this is of course a little ridiculous because I mean if you instantaneously turn it on a QAM receiver, you first have to synchronize, channel estimate and all these kind of things. But let's assume in an ideal case we take all that out and then basically have a very conservative estimate of the front end. Then we do our whole nice mathematical optimization. And then we land here. This is an example of minimum energy per bit. At an effective rate, you see the x-axis, the effective rate, of 400 megabit per second. That is not that slow. The green area turns into blue. That means unipolar impulse radio up to 400 megabit per second is the most energy efficient way to go. And we can achieve a couple bits per second per hertz with unipolar impulse radio. It's not like it's 0.01 bit per second per hertz. And if we look at true networks, the capacity in our true networks outside, most of the time in most of the areas is less than a bit per second per hertz. We have ample of spectrum. Not necessarily in some hotspots, I know that. If you're in a soccer stadium watching a game, whatever, all that's different. Then we have a whole area up to 10 gigs where zero crossing modulation is best, and only in the top area should we start doing QAM and then maybe NOMA. This is from an energy optimal point of view. So I don't want to go through the details. We have all these different details, all these optimization tools. We look at this at different frequencies, 2.4 at FR3, at 7.75 gigs, and at 60 gigs, millimeter wave, to see how these different things are optimal. And these are some preliminary results we published. In the meantime, with a little bit of help of RF chip design, we've managed to show that you can actually gain at least 100x. That's to be published soon. So what does that mean? That means if we look at this, actually, we had an energy problem with 1G. It was big, clunky, heavy energy. 2G came up with a new radio access network and solved the energy problem. Then we thought 2G we can scale like CDMA, IS-95, we just can scale to 3G. What did we find out? Holy moly, what an issue. We had a huge energy problem. 3x power consumption increase in the network. So we came up with OFDM. Fantastic. It was so great that when 5G was standardized, everybody said, let's stick to it. It was so great. And what did we find out? 3x increase in power consumption of the radio access network. A big problem. And now we need another solution. As I say, the gearbox doesn't say we kill OFDM. We just use it exactly when it's necessary. And then use other methods in other cases. This is our proposal. Hopefully you come up with other proposals. I think we just have to have a fresh look at this and really think of it, understanding the implementation of our signal processing and so on. Now, the other part, obviously, is consumer, is the robots. I said personal mobile robots, and what is the most visible personal mobile robot that we can think of? It's the autonomous driving car. Okay. So how do we approach that? It's not only the connectivity. I mean, the big power hog there is the AI. Yes, if you think of the first Teslas, if you chose this autonomous driving mode, which was just assisted driving, as we all know, The power consumption of the AI and the sensor system basically was such that your range decreased by 3 dB. Half of the power went into that. And if you look at modern systems today, in many of the cars, this is still the case. If you turn on full ADAS, everything, the range is reduced by 3 dB. So, but what we really want to have is we want to drive during storm, at night, after dinner, after drinking. We want to drive in really harsh environments. And the systems we have today, it's just good for sunny weather and dry streets. As I remember, when I took my rental Volvo XC90 from Dallas to Austin, it nearly killed me 3 times, because what did it see? It just had rained, and there was the asphalt, it was concrete slabs, and the black asphalt between the concrete slabs was shining in the sun, looked like white lane markings, and it always thought these are lane markings and wanted to drive me into the center divide. Thank goodness I was strong enough. I really needed force. After that, I've never gotten in a Volvo again, on the driver's seat side at least. For me, that's too unsafe, but everybody has to choose their poison, and if you choose a Tesla, that's the same. The good news on the Tesla, however, is that, as you know, the automated driving feature is turned off before the impact, so that the impact doesn't happen with automated driving mode turned on. Save the statistics. So how safe is safe? And we have to think as engineers, and I'm going to be even more brutal. I'm going to say AV cars have to be 10 times better than humans. And to have some statistical significance, and driving in France is very different than driving in Germany, than driving in Switzerland, than driving in China or the US. So we have to look at country by country, because the styles are very different. What does that mean? We have to have at least gathered 100 dead people by impact, by automated driving, to say this is statistically safe, because if people were driving, 1,000 people had been killed. This is how we have to look at it. Now, if you look at the statistics, what you find out is that German driving is, in these 4 countries, is the safest. That means in Germany, we have to visit every single meter of road 1 million times to get to this kind of statistics. That's the amount of data you have to collect. In Japan, 500,000 times, if you look at the required road visits on the right column. In the US, only 18,000 times, and in China, 2,500 times, because the deaths per kilometer are very different in these different countries. But still, we have to gather all this kind of data to get this kind of statistics up and running and make sure that automated driving is really what it's supposed to be. But then we also have to build this kind of an AI engine. And what is AI? It's just signal processing. It's a nonlinear adaptive filter. So let's go to it. Signal processing, what do we need? We need linear matrix algebra. That's what we love. Basically everything, not everything, but many of our stuff, the things we do is about linear matrix algebra. Now, linear algebra is based on basically 2 operators. That's the main part of linear algebra. You have inverse operators, whatever. But in the core of the heart, it's just we need a semigroup with a semigroup with operator 1 and a semigroup with operator 2. Operator 1 has to be distributive over operator 2. Even we can have operator 1 only be left distributive over operator 2. We can restrict it, getting to the bare bone of linear algebra, if you look into the details. And then we can do the distributive law. And if we have 1 and 2 being multiply and add, this is a typical thing that we know. But this is basically what is important. So then we can build these same equations with matrices, and if we have this kind of matrices and time index k plus 1, then we can do this kind of recursion. Then we have look-aheads, and everything is fine, and we can sort of build systems without worrying about bottlenecks, not worrying about data rates and things like that. And the very early part, without algebra, of applying this idea to Viterbi decoders is what I did present in 1988. And then later, we looked at the generalization, and two operators can be as funky as plus and ln of e to a plus e to b. Yes, so you have all kinds of different linear algebra operators that exist. Now, if that is the case, what is so different in AI? And if we look at an AI network, we have nodes, we have arches, branches, whatever, similar to any filter if we put it down, and the different state variables in a filter. And we have matrices connecting this, AK plus and AK plus 2. Fantastic. What's the big deal about it? The problem is the third operator, the nonlinearity. And it can be any kind of nonlinearity. Let's call it a ReLU just to make it simple. And the ReLU we can put in as a max. So then, okay. If we have this kind of third operator, let's just plug it in. Because the generalization of this equation for three operators exists. I mean, this is old stuff, cold coffee. So we can write these equations and start compacting the whole AI engine into one big matrix, right? Sorry, no. The problem is that if we go and build these kind of matrices and have ABC, and we want to do this kind of operator statistics and operator operations, what happens is no. This is where linear matrix algebra ends to date. With three operators, we have no clue today how to handle this in one generalized nice theory and do all our nice transformations. And this is why we have the issue. This is why we cannot simplify the operations. And we have to feed all these stupid, sorry for saying it, but these massive, gigantic coefficient matrices into our AI engine. And so the whole problem of AI is not multiply, accumulate. It's somehow finding these coefficients and jamming these coefficients in there. Think of this network. These coupled states, that's not a big deal. But all these branches, and every branch has different coefficients. And that is where the problem pops up. All these coefficients. So if we have this implementation challenge, what do we do as signal processing people? Now, I was approached 3 years ago by BMW and the whole consortium saying that we've done pretty good on designing signal processing chips for wireless. Why not do this for AI? I said, me? AI? I am not really an AI engineer. But let's have a look. So we took up the challenge and they said, we have to beat Tesla with their AI accelerator. Okay, that's the consortium. Obviously, what they need to do is sensor fusion. You have super high energy compute, energy efficiency, high compute performance, low latency. Low latency is really important in this context. You cannot just send it to a server and wait for the reaction because the car has to react left, right, or center. And so it's about cameras, 16 cameras doing image pre-processing, early sensor fusion with radar and LiDAR, and then AI object detection in this kind of an ASIP or ASIC, and then finally late sensor fusion, and then the parameter estimation. Here's the chip. We taped it out. We have it in our hands since early this year. And you see that the AI accelerator is the rose and violet part of it. It's about 17 square millimeter, and this is the whole chip architecture that you can see here. So the camera input and all these different things are there as well. If you look at that, there is our custom AI accelerator on the top left corner, and we put in the industry's competitive standard of that time, the Extensa CNN accelerator from Cadence, and of course an application processing unit and big ARM core sitting there as well. Then we have safety islands. We have pre-processing with the videos pre-processing on the chip. And we have internal and external memory, DDR4 interfaces. We can process up to 16 cameras, a couple LiDARs, and at up to 8 radars. Now, the aim is, if you have this, how do you get there? Well, this is where we got. And I'll sort of tell you a little bit about how we got there. This is the optimized processor from Zhang et al. Yes? Then we have the one here optimized by MediaTek, which is in the handsets today. And then you have the Eusipco chip. And you see, we optimize for throughput, adaptivity, advanced features, but energy efficiency, that was so important. Well, we had to make sure that we got the latency up and running. But what did we do? We have a fully adaptive system. We can do 7-bit, 3-bit, 4-bit computation. So with these advanced features, we can get our energy efficient down. What is the whole idea? The whole idea, if you look at it here, is a bit serial architecture. And why is bit serial in the context of AI? I mean, this thing seems like going back to the 80s of chip design. Bit serial. People laughed about us at first, laughed at us. It's scalable, can all do all these different things. Now, the one thing that you have to know, which is really important, is in AI, not every coefficient is non-zero, plenty are zero. So you want to make sure not to do multiply accumulate for those where the coefficient is zero. So everything is about address generation and grabbing the right data out of memory in some kind of funky way, jumping around in your address in a structured way. So you need to do dilated convolution, you need to do those transport convolution, depth-wise convolution, 1D, 2D, padding, pooling, etc., all these different things. And so you need a control unit that makes sure that all the data is grabbed at time and the coefficients are grabbed at time, does the scheduling, and does this network processing unit acceleration control. And this is basically our neural processing unit that does this with a local memory and then grabbing the data from external with a DDR4. In a dilated convolution, just for you to know, this means I have many of zeros. I just jump around once in a while. And how do I make sure that I can jump around that way? This means, again, address generation. Now I need time for computing the next address. What is the beauty of bit serial? I have time. If I'm 4-bit serial, I have 4 clock ticks to do this. And so I can build a super efficient memory address generation grabber interface. And this is what we did. So it's minimized computation, no zero value computation. Memory reads, yes. Make sure the DRAM bandwidth is used as efficiently as possible, because every DRAM read is power consumption. Address generation is really the major complexity. So the solution is bit serial. And then we even, in dilated convolutions, you can show here with a dilation rate of 4, for example, we're almost an order of magnitude better than the competition. Here is basic some details. It's in 22 FDX. It's not a most advanced node. Global Foundries, manufactured in Dresden. We used IP blocks from Synopsys, Dreamchip. The cores, as you know, came from Cadence. The other neural processing unit, we have ARM cores, RISC-V, etc., etc. The hardware of the AI accelerator is done by my team, 3 people competing against that $1 billion team at the other companies. The compiler comes from the University of Hannover, Holger Blume's team. Holger you probably know from many different conferences as well. About 1 gigs clock frequency, and if you look at the comparison, an ISSCC 20, that's the MediaTek chip. And then we took our 22 nanometer Eusipco chip and normalized it to 7 nanometer. Then we are in teraops per square millimeter 4 times better. In total teraops, 2 to 7 times better. And TOPS per watt, if we don't use the dilation and not the bit serial, not the 7-bit, 4-bit, whatever kind of, then we are 0.7 times, but up to 3 times. So in total, teraops per square millimeter in watt, that's sort of a measure that we use. It's 1.1 to 4.2. We have ideas in the pocket. I'm working on it now for a 10x improvement. And now the companies are knocking on the door, just like at last Eusipco conference that was here in Grenoble, where Fujitsu came and knocked on the door. Finally, the last part I want to talk about is when we implement things, we forget one thing. It's trust. And this is something, dear fellow members of our community, fasten your seatbelt. Make sure you have an airbag. We have to build our systems to be trustworthy. And this is something which is, I think we're at the beginning of this, just like when Hartley started defining information. And then Shannon, with all the previous guys working on it, and Shannon then came up with his version of it, and that took off like crazy. But I mean, Shannon would be nothing without all the other people working on it before. We have a similar situation. We have to understand we're at the very beginning of understanding seatbelts and airbags for signal processing systems, making them trustworthy. What does that mean? If we go through a crowd like that, we don't assume people are going to stab you in the back. We just trust them. Now, if robots are whizzing around, we have to be trusting them 10 times more than humans, just like in a car, 10 times more than humans. So in the end, what do you want to do? When you get vaccinated, you'd rather go to the robot than to the medical doctor because you trust them more. That's our goal. It must be our goal. The same way as people, but even more than people. But what does that mean? Well, let's look at this. This is a physical device. We're now at the door in the advent of mobile robots. There's so much AI, wireless communication, sensing, signal processing happening there. Here we have an example. This was a physical device connected, not mobile yet, that took off like crazy. Think of it. I mean, it was like the hottest stock on planet Earth. And then what happened? A little kid got on it, fell down, and was hammered to death by the pedals. That was the first impact. But what really killed the prospect was Hollywood. They came up with one sequel in a murder mystery series where somebody hacked into this system and the other guy got a heart attack because of it. Yes, because, this is how he killed him. And the result is this stock performance. It's penny stock now. And that means we are now in the area, at the doorstep, in the era of entering mobile robotics. And how do we make sure that we trust these devices? Then we can go to social sciences, humanities. We've done that. Yes, Mayer et al. In '95 published something very nice because we signal processing people like block diagrams. So there's factors of perceived trustworthiness, there's trust, there's perceived risk, acceptance of risk, outcome, and then some feedback loop. This is how humans interact with humans, not humans with machines. Okay, so there's already a difference between trustworthiness and trust in this model of social sciences, which is used highly. Then let's have a look. What could be factors of perceived trustworthiness? Confidentiality, integrity, accountability, authentication, attestation, and privacy. So the BSI, the German cyber agency, asked us to do a study on 5G and on ORAN, 5G ORAN. And this is the study. Let me explain this. What does that mean? We put in C is confidentiality, I is integrity, A is accountability, Z is Zurechenbarkeit, yes, and P is privacy. So You see here availability, accountability is Zurechenbarkeit in German, so that's the Z. But what do we do in addition? So we looked at these different items of a 5G and a ORAN network. And we looked at this, you see the two horizontal lines. Best case ORAN, worst case ORAN. Best case means turning on all security features that ORAN gives you. Worst case, only doing minimum, bare mode minimum, nothing beyond what you must do. Same thing for 5G, 3GPP. So best case, worst case. So the top left corner turns out to be best ORAN, best 3GPP. This is best ORAN, worst 3GPP, worst ORAN, best 3GPP, and worst ORAN, worst 3GPP standard. Now, the result is this. And the plus is in there in those buckets when we even found a way to hack into the system. That is how we design systems today, just purely for functionality. So we're always thinking of performance, performance, performance. But think of selling a car that doesn't have a safety belt. Would not be possible anymore. Without crash test, would not be possible anymore. I think with personal mobile robotics, we're at the doorstep of having to understand how to design trustworthiness into our systems. So how do we design trustworthiness by design? So we have to come up with a model. And this is just a model we put on the table. It's like partly putting on his idea of what information should be. Yes, I don't say this is the Shannon idea, no way. I'm just saying we have to work our way over the next decade to get to some kind of a model where we understand how to build trustworthiness into our signal processing systems. And the objectives have to be such that they can be neutrally measured again and again, that privacy, security, integrity, resilience, reliability, availability, authentication, benevolence, safety, etc., are designed such that they adhere to the expectations. And of course, security, if somebody comes up with a new hack, maybe the security of 7.8 drops to 2.1 or whatever, I mean, that can happen. Then this, of course, is then in action. We have to hope that all this is there, measurable of our system, and then we weight this, just like in a neural network, we weight this and in a nonlinear way, add this up, look at the assumed risk, the perception, the situation, the state, the competency, the experience, and then, oops, sorry, something happened here. And then, obviously, these objective characteristics of trustworthiness are such that we don't want to do them, measure them all ourselves. We want to maybe rely on certifiers, auditors, agencies, etc. Like when we went to the rental car agency, we're not looking if it passed the smog test, it passed the physical test. We just assume that it has been because that car rental agency is trusted. So we have mediators doing that for us. And then, based on that, we decide, or the car decides in the center lane to turn to the left lane or to the right lane. So there are actions. And these actions are not neutral. So on the left, they're objective. Everything red is subjective. It's based on your situation, your state. Then there are results and learnings fed back. This whole thing we put into one paper just to give it an idea, to put it out in there, to get it started, the discussion. And I'm really into this. I really believe we have to do this. I convinced the state of Saxony to start a research institute in 2018. In the meantime, we're 90 people researching on this. We design our own processors, our operating system, our software system ideas, wireless, and the internet. This is besides the Vodafone chair, the Backhausen Institute, where we're trying to understand how to design trustworthy systems. Now, obviously, we need 9,000 people. I don't want to have 9,000 people reporting to me. 90 is more than enough. I would like to rather have 9,000 people on planet Earth picking up this idea of that we have to really start thinking in this way. We convinced the German government to put in close to 90 million euros for applying this methodology to medical devices, because medical devices are very small. You know, an MRT, a CRT, it's a small device compared to a networked car in a system with other cars around it, or a cell phone in a cellular system. And we have all the electronics industry and all the medical industry combined and experts, and this is where we are. So in conclusions, what we see, these are platform chips I can show because we designed them over the years, and many of them, the 1997 one we designed, and that was the basis for starting Systemonic, etc. Samira was the one for starting Dresden Silicon, etc., and some of them for Blue Wonder and others. So we have designed all these different platform chips where we really have the multi-processor system on chips with custom processors, ASICs, ASIPs, general purpose processors sitting on there, microcontrollers and everything like that. Our newest two are those that I show on the left is the Eusipco chip for the AI processing, where we're just again doing performance, but in parallel at the Barkhausen Institute, we're also starting to build platform chips that have embedded trustworthiness with isolation mechanism, an operating system that is provable, secure, that you can formally verify, etc. So how do we build these kind of trustworthy chip so that, and what are the restrictions? Because it doesn't come at zero cost. It may not cost more than 5%. An airbag and a safety belt doesn't add more than 5% to the weight of the car. The crash zone does maybe once in a while, but still. So we have to design these systems such that they are minimal cost for maximum functionality in terms of trustworthiness. So the challenge ahead is really continue low power, low cost, high performance system design, but really merging these two worlds and bringing trustworthy platform chips to reality with our beautiful signal processing algorithms sitting inside. Thank you very much. I can take questions. Yes, I stopped on time. If you want to ask questions.
And there are microphones.
Yes, thank you for a very good talk and a big perspective on the field. Very much appreciated. I would ask a technical question more related to that.
Go ahead. I didn't show you the equations.
There are lots of opportunities to ask questions, but yeah, one related to signal processing, because I very much agree that progress of signal processing started with linear algebra, and then this appearance of the third operator destroys all the properties we usually use for deriving very sophisticated signal processing algorithms. And then you went to chip implementation right away, but there is an opportunity for signal processing researchers there, and I think partially it's exploding multilinear algebra. In multilinear algebra, we don't have many properties as we have in linear algebra, also destroyed, but what we have is a decomposition. And by doing decomposition, we can minimize the number of parameters to be traced very significantly. And another is, of course, what people in computer science already realized, like graph networks. It's like enforcing a certain type of kernel in your data, which also leads to better accuracy minimization of the properties. But I specifically wanted to advertise multilinear algebra and also hear your perspective on that.
No, I think honestly, there is still so much room for expanding beyond the regular linear algebra. Absolutely, you're totally right. If it's multilinear algebra, if it's tensor algebra with all kinds of funky operators that you can use, etc., etc. And I think what we see a lot is that it is done without understanding that the beauty of some of this also lies in its ease of implementation. And that's where this is a little bit of a call for it, saying that sometimes we get so excited about our math. I mean, why did I study electrical engineering? Because I wanted to do math, honestly. Yes, I got excited in mathematics. Mechanical engineering was not for me. And then we get so excited in that we forget sometimes the beauty of using some of these tools. And you can take a little nudge left and a little nudge right in your theoretical research, and the one nudge has a big bang implication on the implementation, and the other is totally stupid. Sorry for saying it, for an implementation point of view. And that is sort of why any PhD student that is working on theory in my team has to attend my course in hardware, software, co-design, and how to design chips, and pass with a good grade. Otherwise, I don't accept them as PhD students, no matter what kind of beautiful theory they think they want to do. Because if you're not grounded, I think you lose so much of the engineering part. Because, I don't know, as an engineer, the most exciting thing for me was when people held my product in their hand. I mean, that's so much. That's the biggest reward on planet Earth for me. Yes, and that's why when Berkeley approached me, they wanted me to become a professor when I was living in California. I said, no, I cannot become a professor now. I don't know of any customer holding my designs in their hands yet, because I wanted to have this kind of level of experience. But everybody's different. I mean, there's not one prototype. I mean, we also need these pure theoretical, super-duper experts that really can build new theories in a way that maybe 20 years from now become valuable. There's a question back there, if you shout loud enough.
Hi, thank you for the very nice talk. I have a question on this trustworthiness aspect, right?
Yes.
So you were using a lot of those parallels to cars, and you know how cars are safe because they have the belts, the airbags, but you know, I would say that the most unsafe thing about a car is a driver, right? We have a certification for that. We have a driver's license, but I would argue it's like the least, like the weakest certifications compared to all of the certification that the car has to have. And then when you transfer this to the chip, what you are talking about is the security and trustworthiness of the execution environment, not of the algorithm itself. So what would be, you know, the ways to ensure that we can actually trust the algorithm and not only that it's executed in a secure environment?
Yeah, so let me try. Oh, it doesn't work, this feature on this phone. Yes, because I mean, you talk about the driver. I know, and that's why I basically showed this slide. Because, I mean, if you look at it, in Germany, there's 10 to the minus 9 deaths per kilometer. And in China, there's 10 to the minus 5. And it's humans in both countries. Yes, you're absolutely right. There are differences in drivers, in countries, in emotions, in whatever all, mode of operation. But in the end, we have to design against these specs. We have to design such that we're 10 times better than a driver, than a human. If we walk with our robot walks through a crowd, we accidentally step onto people's toes or bump into them accidentally. We say, excuse me, look into their eyes and say, excuse me. Now, how do you trust a robot that looks into your eyes and says, excuse me, that doesn't even have eyes, just quacks, excuse me, and then continues on and you believe it? No, that means the probability of incidents really has to be 10 times lower than with humans, because no matter in which country we live, we just scale to the way other humans are and other humans react and act, and this is something which we have to learn.
So basically you're saying that the ultimate certification is just empirical evidence. We have to drive those 1 million times the number of roads in Germany, and then we know if we can trust it.
Exactly. If you achieve in this 1 million times less than 100 dead people. Yes, I mean, that's basically the goal. Sorry for putting it in such terrible implications, but that is what we have to do. Now, this is the driver thing, and a robot walking along the street hopefully is not going to kill people, but maybe injure a person or scratch their legs or arms or whatever all accidentally, and we have to make sure that that doesn't happen, or that happens 10 times less than accidentally humans bump into people.
Thanks.
Thank you for your nice presentation. When you talk about truthfulness, which aspects are you able to translate into equations? Because that's what we like to deal with as signal processors.
Exactly. Perfect question, thank you. So, just like when the whole world in the early 1900s was in search of a definition of information, it was not only Shannon, there were dozens, hundreds of people searching for a definition of information. It was known as an open topic. I listened, I'm one of the students of Jim Massey's Applied Information Theory lecture at ETH Zurich, and we had to go through the whole history of that, and he showed us all the history of that to put things into perspective. Then we have to understand this is exactly the call. So how do we put this into equation? In the case of security, we can say it needs these and these many computations, like 1 billion or 1 trillion or 10 to the 48 number of computations to hack into a system. And then we can say it's trustworthy, unless somebody comes up with a new algorithm and suddenly you only need 1,000 operations and you can hack into the system. So we have to have different measures in different categories, yes? And security, in terms of crypto security, that's relatively easy. In terms of privacy, or as some British say, privacy, this is a different case. In that case, we might, because how do I keep things private? Today, if I accept my Google Maps, I accept the terms to override GDPR. And GDPR says you're not allowed to combine the identity and the location of any person in any software, in any device. What does Google Maps do? It merges them. Do you need that? No. Google doesn't need to know my identity. So how do we make sure that we keep like the GPS data in an homomorphic encrypted fashion or whatever else with a separate key, separate in such a way that our GPS data and our identity are encrypted in different ways such that only somebody that has a key can combine these, that has gotten this key from an authority. That might be an approach. I'm not saying that is an approach. Then again, you can say, okay, how difficult is it to hack into these kind of keys and whatever all. So we have to look at every single step on its one by one to understand how to break this down. Just like this, I think, is way more complicated than defining information theory basics, because we have all these different objectives, characteristics of trustworthiness. There's an IEC standard on trustworthiness now out there based on these characteristics, just as we had put them out. And this list is not finite, it's ... So how do we make sure that we make these all measurable, that they become objectively measurable, and you measure them the same way as I measure them, as somebody on the Fiji Islands measures them. And then we can make sure that they're measurable, and then we can build these kind of systems where we have this level of trustworthiness. So it's not only measuring information, it's measuring many, many different aspects. And that makes it complex, I totally agree. We're at the opening of the can of worms.
So we are in France, and Patrice has just said to me, perhaps we should respect the coffee break. So let's thank Gerhard once again for a wonderful talk. And you can go to the coffee break.